Hey guys, Levi here. Welcome back to my channel. In this video, we'll be looking to solve a work and energy related problem. This is a dynamics problem. This is part of the FE review session. Once again, feel free to like, subscribe, and share. And if you have any question, do not hesitate to comment in the comment section. Also, if you want me to cover any other concepts, please feel free to ask as well. All right, without further ado, we'll get started. The problem reads as follows. The 10-kilogram cart shown in the figure is accelerated from rest by force along a smooth incline for 5 meters until it clears the top of the ramp at a speed of 5 meters per second. The value of the force in Newton is most nearly option A, 21, B, 26, C, 32, and D, 64. So before getting started, I would like to highlight a few clues that are given right away, just so we know what approach to have on this problem. This is one thing that I like to do with all the dynamics problem, given that they can, become very complex and very complicated to where like you don't even know where to start. So the very first thing that I like to highlight here is the fact that the cart is accelerated from rest. So we know that the state one of that cart is rest. The second thing that I'd like to highlight is the fact that this is a smooth incline. And what that means for us is that we will not have to worry about friction. All right, so now that we've highlighted these two items, we're gonna get started. So, as I mentioned before, this is a work and energy related problem. So if you're not familiar with the work and energy relationship or equation, we can pull up the FE review handbook, FE reference handbook, pardon me. So I've searched from dynamics and just started scrolling down up until I landed on the principle of work and energy. As you can see here, I've highlighted that if V initial and V initial are respectively the kinetic and potential energy of a particle at state I, which is pretty much, to relate it to our problem, this is the initial state, then for conservative systems when there is no energy dissipation or gain, the law of conservation of energy is T2 plus V2 is equal to T1 plus V1. However, notice that on our problem we have an external force that is exerted on the cart in order for it to move. So this will be the equation that we'll be using. As we can read here, if non-conservative forces are present, which is, once again to relate it to our example, that force is not conservative, then the work done by these forces must be accounted for. Hence, the equation that we had initially there changes from T2 plus V2 is equal to T1 plus V1 to T2 plus V2 is equal to T1 plus V1 plus U from 1 to 2, which is the work done by the non-conservative forces in moving between state 1 and state 2. So one of the things that they've pointed out also is that we have to take care during computation to correctly compute the algebraic sign of the work term. If the forces serve to increase the energy of the system, then it'll be a positive. However, if the forces such as friction serve to dissipate energy, then U from 1 to 2 will be negative. Okay, now that we've covered that part, we'll get back to our problem. So we'll write down the equation. Okay, So we have T2 plus V2 is equal to T1 plus V1 plus U, or rather, yeah, we can either mark it as work or as W or U, but this is going to be U from 1 to 2. This is the equation that we'll be using. So now the next step will be to plugging our numbers into the equation. Our given are the mass of the carts, which is 10 kilograms. We have the displacement of the carts, which is equal to 5 meters. We also have the speed of the cart, or velocity rather, so that'll be 5 meter per second. Okay, and we know that gravity is equal to 9.81 meter per second squared. All right, so plugging in our number, so we know that, as we've highlighted before, the cart is initially at rest. Therefore, this side of the equation, T1 being the kinetic energy, is equal to 0 since our cart is at rest. Since there's also no elevation at rest, the potential energy is equal to 0. However, the work that is being done is going to be equal to force times displacement. And T2, or kinetic energy in state 2, is equal to 1/2 mv squared plus V2, which is our potential energy once the cart is pretty much at this step. So we'll have mgh. So we'll plug in those numbers as well. So we have 1/2 times our mass of 10 kilograms times the velocity of 5 meter per second squared plus the mass 10 kilograms times gravity, which is 9.81 meter per second squared, times the height at which will end, which is going to be 3 meters, will be equal to force times the displacement of 5 meters. So 5 meters times F. Okay, so we'll plug in these numbers in the calculator and see what that gives you. So cancel these. We'll have 125 kilogram meter squared per second squared plus 294 kilogram meter squared per second squared is equal to 5 meter times F. So this is 294.3. So summing this up gives us 419.3 kilogram meter squared per second squared is equal to 5 meter times force. We can simplify the meters here. So the force will be equal to 419.3 over 5. And as far as the units, we have kilogram meter per second squared and as we know, this is equivalent to Newton. And again, I'm gonna emphasize on that. It's very important to leave the sign while you are solving your equation, you know, just so you can see how things cancel out. As I mentioned in my previous videos, some problem may be tricky where like do you even have mismatch units to where like you have to do a little bit of conversion. So if you don't catch that initially and that you just, jump right into the problem and start solving, you will end up finding an incorrect answer. So, however, if you were to like write out all your units and as you're solving the problem, once you get to the end and you notice that, you're not getting whatever you're supposed to get, then you may, find out that you may have missed a conversion, somewhere earlier. So, plugging this number in the calculator will give us, so 419.3 divided by 5 gives us 83.86 Newton, which is equivalent to 84 Newton. And looking at our proposed answer, this should have been answer D. I meant to put 84 there rather than 64. Thank you and see you on the next one.